In the last class, we tried to understand the criteria for the chemical equilibrium. So, I recapitulate a bit. Uh, we have seen the condition required for adiabatic closed system, and we have seen that the change in entropy is positive for the process, and for the equilibrium condition, the change in entropy is zero. That means the entropy is maximum at the point of equilibrium that we can see here at this peak. So the equilibrium will be achieved at this peak point. And if the process is non-adiabatic, then it's a more general case. Therefore, in that case, we have derived it, and we have seen that for a particular temperature and pressure, the change in Gibbs function is negative for the process, and at the equilibrium, the change in Gibbs function of the system is zero. That means the Gibbs function becomes minimum. So these are the two conditions that we have seen in the last class, that the equilibrium condition. Okay, that can be called as the equilibrium criteria. So from the thermodynamics, from the second law, these are the conditions that we have seen. Okay, and beyond this, there is violation of second law. As we can see, that dashed lines indicates a violation of second law. That means for this situation, which is the general one, where dg is positive, so it is not possible, that violates second law. And for the adiabatic situation, beyond this point, that is beyond this equilibrium composition, the process is not possible. That is due to violation of the second law that we have seen in the last class. Okay. Next, what we will see, that what is the equilibrium composition. Okay. Now, this condition gives a general one. That means irrespective of the reaction, whatever be the chemicals involved in the chemical reaction, this is the condition. That is, dg at a particular temperature and pressure must be negative. Okay. Now, if we consider a particular chemical reaction involving two reactants A and B producing two products C and D, so in that case, if we consider that equilibrium has already achieved, and during that, if there is a small or infinitesimal amount of reaction taking place, that means a very small amount of component A and B are consumed, and very small amount of the products C and D are produced during this small or infinitesimal chemical reaction. In that case, if we try to write the condition or the equilibrium criterion, then we can write that change of the Gibbs function at a particular temperature pressure, that means at this constant. Okay. Now, in this case, if we just apply the equilibrium criterion for this example reaction or sample reaction, then we can write for individual terms that we also have seen in the last class, that in terms of the particular reactants and products, we can just elaborate this. So dg is the extensive property, and that extensive property in this term we have written in terms of the components. Components means including the reactants and the products. And then in the third term, we have written in terms of the property that is intensive property or the molar property. So per unit mole basis we have written. So that is a product of the molar, that is total Gibbs function change is equal to the Gibbs function per unit mole multiplied by the change of the component or the change of the number of mole of the component. So that we have written, and this is at a particular temperature, and that is specified temperature and pressure. Okay, I guess it is clear. Next, we have just expanded this term for four components. So simply here we have four. If we have any other reaction, then we will have accordingly number of terms. So you have to understand that number of terms here are four. That means A, B, and A, B, C, and D. So A and B are reactants, and C and D are products. So accordingly, all the components you have to take. That means taking into consideration the reactants as well as the products. Okay. Next, what we have seen, we have written the stoichiometric reaction, because at the equilibrium condition, this reaction is very infinitesimal, and that will be according to the stoichiometric reaction. Okay, so that will help us in understanding the amount of A or number of moles of A that is generated, number of moles of A that is consumed, number of moles of B that is consumed during this infinitesimal reaction, and number of moles of C that is produced, and number of moles of D that is produced. So this will be in accordance with the stoichiometric coefficient. So they will be proportional to the stoichiometric coefficient. And the proportionality constant epsilon is a very small number. So because this reaction has already achieved this uh, chemical equilibrium, and therefore if we just consider a thought experiment as if the chemical reaction at the equilibrium condition is disturbed a bit, that means it is shifted a bit in equilibrium condition, and then it is kind of trying to re-establishing the equilibrium condition. That means at the equilibrium composition or the equilibrium condition, it was already established. Then we have that means we are considering a small reaction to re-establish the chemical equilibrium. So that way, how much amount of A will be consumed, how much amount of B will be consumed, how much amount of C will be produced, and how much amount of D or the number of moles rather will be produced. So that way, now we have written this one, the criterion for chemical equilibrium, that you can see highlighted. So remember that this is for this sample reaction only. The main equilibrium criterion was written here. So this is the chemical equilibrium criterion, the most general one. That is the mathematical form is this one. Only for this sample reaction we have written, expanded this, and this is the one that is written in pink. Okay. So that was done. Now what we will see is in the next page, we will try to understand what will be the basically change of Gibbs function. Now, because you see that here the Gibbs function, at a particular state. What is that state? Temperature. That you have to follow. That at this line, at this pink equation, you see that here you have GC bar, GD bar, GA bar, and GB bar. What is that? That means basically they are the molar Gibbs function of the components. Okay, that means what? They are basically any chemical, like say in a chemical reaction of say CH4 plus O2 is equal to say CO2 plus H2O. In that case, accordingly, A, B, C, D we can identify. Now, what we have to basically use means to use this, what we have to get GC at that particular temperature and pressure, GD at that particular temperature and pressure. That means now our target is to know these things here. Okay. So it must be followed properly. This one. So these terms we have to get from the table. Okay, and how to get this next job will be to know that. And these stoichiometric coefficients are already known, because if I know the chemical reaction, then the stoichiometric coefficient can be easily known. Okay, so is it clear? Therefore, GC, GD, GA, GB, these we have to derive. That is our target next. Okay, next what we will see is how to get that reaction. Okay, you see that this is the reaction, this one. Now we will try to see how that reaction comes. Okay, can you see the middle of this page? So this is the reaction that we have there. Sorry, this is the expression of, you see that G bar I. G bar I means what? G bar of a particular component, say A or B or C or D, whatever. So this is the term that we want to calculate in terms of something which we can get from the table, or which we can calculate from the known properties. Okay, so you see that right hand sides are known from either the table or from the properties we can calculate, and the left hand side we will basically put in the chemical equilibrium criterion. Okay, so that we will see now how to get this relation. Okay, now we will see this one. So I think it is seen. Now we will see here. You see that what is Gibbs function. Now you see that we are writing in terms of the molar properties. Simply molar properties, it is similar to mass basis. Okay, simply it is total property divided by number of moles instead of number of mass, is amount of mass or kg. Okay, so we know the definition of molar Gibbs function, that is G bar is equal to H bar minus Ts. Okay, Ts bar, right? So these are basically the molar properties. Okay, next. Okay. Next, you see that G bar, H bar, and S bar are the molar Gibbs function, molar enthalpy, and molar entropy respectively. That is per unit mole basis. Okay. Next, there is a conversion from mole basis to mass basis that you can see. Simply, if I multiply the mass-based quantities, that is specific quantities, with the with the molecular weight, then we will get the mole basis term. So I think it is seen. Yes, I think it is seen. So G bar, H bar, and S bar, the Gibbs function, molar enthalpy, right? Next, we have converted this. Just shown the conversion factor. If you need to convert, simply multiply the mass basis with the molecular weight, because mass basis means it is per unit kg, and molecular weight means what? Uh, I'm sorry, I think there is a mistake here. Uh, there is a mistake here, I guess. Uh, just it will be, I think, the opposite. Let me just check once. It will be, uh, you see that molecular weight, what is the unit? Molecular weight. Molecular weight means basically kg. Yes, yes, it is, I think it is okay. Yes, yes, it is right. Because molecular weight unit is kg per number of moles, per kg per mole, or kg per kilomole. And G unit, or say for example, H unit, what is that? Unit of H is kilojoule per kg. So if I multiply these two, kg and kg will be nullified, and therefore it will remain as kg per kilomole. So it is all right. Right, it is clear. So next is uh, again from the TDS relation, what we know is that TDS is equal to dH minus VdP. So that is known from the second TdS relation. Next, again, we can write for ideal gas that dH is equal to CpdT. Okay, so TdS is equal to CpdT minus VdP. So again, we can write that just divide both the sides by T. So we will get ds is equal to Cp dt by T minus V by T dP. Okay, so this is up to this. Next, for isothermal process, what we can write, because we want to specify the temperature, that means we are fixing the temperature, therefore uh, dt is equal to 0. Therefore, we can just nullify this term. It will become only ds is equal to minus V by T into dP. Okay. Next, for ideal gas, we know that P V bar is equal to RU T, where RU is the ideal universal gas constant, RU. So we can write, therefore, just replacing this relation, we can write that here you can see that V by T. So V by T will be RU by P. So simply I have replaced RU by P here. So it is ds, change in entropy, is equal to RU into dP by P. Okay. So we see that ds is equal to this, because you see that why we are considering this, because this is this ds. Again, in the Gibbs function, we have basically ds. Okay, so ds we have to calculate. That is why we are calculating this. So everything should be understood, followed properly. Now, therefore, if I just integrate this, ds means this is a differential change. Therefore, if I integrate this, we will get a change for the reactants to products. That means for the chemical reaction from reactants to products, we can calculate this. So delta S, that is the finite change, is equal to S2 minus S1, where S2 may represent the equilibrium condition and S1 may represent the starting condition of the chemical reaction. So that is the total change. Okay. So that is, therefore, RU is constant, and therefore it will be log of P2 by P1. So that is the integration of dP by P, integral dP by P. Okay. Therefore, again, now I am just, you see that delta S we have calculated by this. Now we will put it in this term, because try to follow that if I just differentiate this, what will it become? It will be let me just okay. You see that it will be dg. What it will become? dg is equal to dh. If I just differentiate this, minus tds minus s dt. This will be this one. Therefore, what will be the finite change? If I go for calculating the finite change, it will be delta G is equal to delta H bar, means all are basically molar, minus T delta S minus S delta T. Okay, so that we have just written here. dg is equal to delta H bar minus T delta S minus S delta T. Okay. Next, we will just put it. Now we will see, we have already calculated delta S. Now, what will be the other terms that we will see? Now, for isothermal process, this is 0 for ideal gas, because isothermal for ideal gas, the enthalpy is a function of only temperature. So if the temperature change is 0, therefore enthalpy will be constant. So that will be change of enthalpy will be 0, and delta T is 0. Therefore, you just put here that this is 0, this, I'm sorry, this is 0, therefore only this term will remain. Okay, so delta G is equal to therefore minus T delta S at constant temperature. So we are fixing temperature here, you see. So therefore now we replace this delta S term from this term, this one. Now we replace. So delta S is minus RU ln P2 by P1 and delta G is equal to minus T delta S. So it will be uh, therefore, I'm sorry, one term I have missed, I guess. Here there will be a T. Okay. This term, please correct this. Here there will be a T here. This T will remain. So a T will be there. Right. So a T, I will correct this and send it to you, the note. Now just correct it. So T will remain here. So T RU ln P2 by P1. Okay. Now see that this is the change of give function at a particular temperature, specified temperature is equal to T RU ln P2 by P1. So that is the quantity we tried to. That is the quantity we tried to. Actually, some students are trying to join, I guess, but since I have muted my mobile, I am just following. I am just continuing the lecture. Maybe I have missed. If someone has tried to join, please. I am requesting them to try again. Okay. Okay. So I think okay. Next is this one. Okay. Now you see that I just now integrate this term. Okay. Now I integrate this term. Okay. Next I integrate this. So one T will be there. One T. Okay. Now you see that GI. Now I just write it in terms of the differences. So it is delta, that is finite change between what? This is the term due to the change of pressure, P2 by P1. Okay. And the temperature is fixed. So change of pressure means what? Pressure from a particular known pressure to some unknown pressure. Okay. Known pressure means what? You see, that is important to understand. Say out of these two, P2 and P1, one is known pressure where the properties are tabulated, and the other one is unknown. So that means if I want to use the tabulated values, then I will use this so that I can calculate the property at some unknown pressure using the properties at the known pressure. So that is the target here. So what I have done is, you see, that is there will be a T, as I told, there will be a T and there will be a T here. Now I have just expanded this term. So this is at a particular temperature. Okay, follow this carefully. This delta G bar at this T is equal to this minus this. So this is equal to Gi bar T Pi minus Gi star bar T and P. So as if this P is known and Pi is unknown. Okay. Now what we have done is we have just replaced this here in this equation, and therefore this is equal to Gi at temperature and no unknown pressure. and GI star at the known pressure. So this is available from the table and this is not known. So I can calculate this in terms of this. And this you can calculate always if you know the change in pressure. Temperature is already specified, so temperature is known. And P2 by P1, these are basically to be calculated. So here basically it will be the partial pressure Pi. This will be partial pressure Pi. And this P1 is the total pressure that you have to know, that you have to understand. So in this relation, P2 is the partial pressure, P1 is the total pressure. So you see that partial pressure may not be known earlier, I mean, a priori. So when the tabulation is done, you cannot tabulate some data at partial pressure because that cannot be known a priori. Therefore, what we have to do is we have to tab. That means the tabulation is done at the atmospheric pressure, 1 atmospheric pressure. Now, how to calculate the data at a particular pressure, which is the partial pressure, from the known pressure at the 1 atmospheric value. So that is done here. Okay. Okay. If you have any doubt, please ask. Okay. So here you see that GI star is the molar Gibbs function of the component I. So I means this component, any component. It can be CH4, O2, like that. Component I at 1 atmospheric pressure. Okay. GI star, this one at 1 atmospheric pressure, that is tabulated. So this is known from the table, and this you can calculate. So if I know the right hand side, I can know the left hand side. So that is the target. And this one is at the partial pressure. So partial pressure means in a mixture, the gas is particular gas or the particular component is existing in partial pressure, at the partial pressure. It is not at the total pressure. So if I know the value at the total pressure, I can calculate this at the partial pressure from using this relation. Okay. Up to now, is it clear? Any question? If you have any doubt, please ask. I think there may be some doubt. So you have to follow the steps. One thing that we want to calculate the change in Gibbs function, because we want to calculate the Gibbs function at a particular specified temperature and pressure, because the chemical reaction is taking place at a specified temperature and pressure. Therefore, at that temperature and pressure, I have to calculate the Gibbs function. Now, if I want to calculate the Gibbs function at that value, knowing the properties at the standard temperature, like a standard condition like 1 atmospheric pressure, then I will be using this relation. That relation is developed like that. Okay. Are you listening?
Yes, sir. Yes, sir.
Okay, means
Yes, sir.
is it clear?
Yes, sir.
Okay, means if you feel any difficulty, please ask. Okay. Okay. So
Okay.
okay. So you see that now you will be following it easily. Now we have derived this. So you see that here in this term, this quantity, this quantity, this quantity we wanted to know. Now we have derived the formula for knowing this quantity. So this is the term which will be used here, 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 and here. And this is the right hand side is the quantity which you can calculate or you can get from the table, because this is known at the standard condition of 1 atmospheric. So by knowing or getting from the table or calculating using this formula, you can get these values. Okay. Now you see what we do. We just replace this equation here in this general criteria. So we just replace it for C. for D. Now remember that this is for ideal gas only because we have used the ideal gas relation already. And some assumptions we have made based on ideal gas relation. Okay. Now we are doing this. We have replaced it here. Okay. Now if I just take these terms out under a particular bracket, this one, then this is related to what? This is related to either tabulated property or the stoichiometric coefficient. Okay. So here you see that this does not depend on the partial pressure, etc. So this depends only on the known property and the stoichiometric coefficients. Now this term is called delta G star T. That is capital G because you see that here you have the stoichiometric coefficient because the number of moles is involved multiplied by the molar function. So it is a extensive property at a particular temperature because temperature is specified. If I change the temperature, the property will change. Therefore, this is a particular property that is called the or change of property. That is called the change of property means what? Change of property from the reactants to the products. That you have to understand. That is the change during this chemical reaction. So that change means the change from reactants to products. So that is called standard state Gibbs function change. That is called standard state Gibbs function change. Okay. Let me just erase that so that you can see it clearly. This is called standard state Gibbs function change. Now, if I just replace again here in this term, so these terms will be written in terms of the standard state Gibbs function change, and the other terms can be written in terms of the partial pressure. You can see there other terms can be written in terms of the partial pressure because the remaining terms contains partial pressure. And you see that since you have a natural logarithm here, so you can raise this because once you multiply it here, the stoichiometric coefficients will be multiplied. And if I just take the power because of this natural logarithm, so partial pressure will be raised by the stoichiometric coefficients correspond for the corresponding components. So we have written it like this. So PC, I think there may be some issue in just viewing it. Is it clear? Can you see it? This term. So it is simply like I'm just writing it so that you can see. It is like PC to the power nu C, PD, that is partial pressure or particular component PD to the power nu D divided by PA to the power nu means the stoichiometric coefficient, and PB mu B. Okay. And it is multiplied by RUT. RUT was already there here. So the coefficients is this. Okay. Next, you see that here, now we define the equilibrium constant Kp for the chemical equilibrium of the ideal gas mixture like this. So that term that we have just calculated or just rearranged, so you can write it like this: Kp in terms of the partial pressure and the stoichiometric coefficient. That is the partial pressure raised to the power by the stoichiometric coefficient. Okay. Now this is replaced by Kp in the earlier equation here. Okay. Now RT, RUT, ln, this is Kp. So RUT ln Kp. So delta G is equal to Therefore, delta G star at specified temperature is equals to minus RU T ln Kp. Okay. Next, what we can do is just divide it. So by this RUT minus RUT, and therefore Kp will be e to the power minus delta G star T by RUT. So that is simple algebraic manipulation. So that we have done. So Kp is this, that is called the that is called the equilibrium constant. Okay. Now equilibrium constants are basically, you see, what is on which the equilibrium constant depends? Can you tell anyone on which the equilibrium constant depends? Can anyone tell? Please try to see this. This yes.
So, Gibbs function.
Huh?
Gibbs function of sir.
Okay, but Gibbs function, you see that it is delta G. It is delta G.
Temperature.
Of course, temperature, and Anurag also told correctly, it depends on Gibbs function, but Gibbs function of what? You see that this is called the standard state Gibbs function change. That means this delta G star T, that is for a particular reaction. And for different reaction, that will be different. Okay. So it depends on the temperature, that is absolute temperature, and also on the particular chemical reaction. Okay. If you change the chemical reaction, then it will change. Okay. So you will see in the table, I will just try to show you the table so that you can follow it. Okay. Now try to see that this is a table for the equilibrium constant. Okay. Now see that I am just showing it from the book by Sengel and Bowles. I think it is a 9th edition book, page number 924. So here you see that it is written for a particular general reaction A plus B, C plus D. And this reaction, you see that it is tabulated for different reactions and for different temperatures. That means this is dissociation of hydrogen. Okay. This is, say, dissociation of oxygen, like that. Now dissociation of H2O, like that. Dissociation of H2O into hydrogen and oxygen. H2O can also be dissociated to hydrogen and hydroxyl radical. CO2 is CO plus O2, like that. Okay. So here you have one combination reaction. So you see that this depends on the particular reaction, and for particular reaction, it also changes with temperature. Okay, that is to be appreciated. Okay, so that means how to see the table for a particular chemical reaction. You will see this table, and you will see that at a particular temperature, what happens to that particular value of the equilibrium constant. Okay, so that is to be seen. Okay, is it clear? Could you follow? Hello?
Yes, sir.
Could you follow that?
Sir. Yes. Yes, sir.
Okay, okay, okay. Okay. Next, you see that therefore, that means the derivation of the property, the derivation of the equilibrium constant is understood, and also how to see the table, that is to be understood also. Okay. So that standard state Gibbs function change is for a particular reaction. Therefore, it depends on the reaction as well as for the particular, as well as the temperature at which the reaction is in equilibrium. That is also to be seen. Now, these are some things that we already know how to calculate the partial pressures. So that is the mole fraction multiplied by the total pressure. So this is number of moles of the particular component divided by the total number of mole. Now we have to understand one thing clearly, that this Ni, remember that this is happening at the chemical equilibrium condition. Okay. So Ni means the particular component, like say methane or oxygen or whatever, H2O, whatever. Now in total means what? In total, remember that in total means at the particular equilibrium composition, it means the components including the reactants as well as the products. It is not simply the reactants or not simply the product. That means if by mistake it may be assumed that Ni, if it is the reactants, then N total will be of the reactants. And if it is for the products, it will be of the product. It is not. Ni is, say, for example, for NH2O, but N total will be considering all the components, including the reactants as well as the products. So it is equilibrium composition, and at the equilibrium condition, the composition will contains the reactants as well as the products. Therefore, in total will be including the reactants number of moles and the product number of moles. Okay, is it clear? Okay. So next, you just replace this in terms of pressure. Earlier it was written. Written in terms of pressure, so I can write in terms of number of moles. Okay. And delta V, delta nu is equal to the total change of number of moles. So here that you have to appreciate that it is calculated with the number of uh, mole difference at the stoichiometric condition. Okay, so that is this one. Okay, uh, so that is this one. Now some I will refer to this in the next class. Now I will try to show you one problem, how to solve it. That will give you some idea, or I think it may be done in the next class, because the problem will take some time. Let me see. Can it be continued up to say 8:45?
Yes, sir. No problem. Yes,
Okay,
sir.
so
Yes, sir.
I can,
No problem.
okay, okay. I can then show the problem. Okay, because it will take some time.
Okay, sir.
Okay. Actually, earlier the book was yes. Now we will try to see one problem, because you have to understand one thing, that the theories can be understood only when we solve some sample problems. Okay, that will be better understood. So now we will try to see how to basically use this. Okay. Now we will see one problem, sample problem. That sample problem is a nice problem. You see this one. So this one. Can you see this problem? Can you read this? As an alternative to electrode. Uh, anyone telling something? Okay, you can mute, because Okay. So okay. As an alternative to electrolysis, hydrogen gas can be produced thermally in accordance with the dissociation process. H2O is equal to H2 plus O2, half O2. Okay. By heating water vapor to very high temperature, determine the percentage of water vapor that can be separated into hydrogen and oxygen when this reaction occurs at 4000 Kelvin and 10 kilopascal pressure. So that means what? We are trying to understand that if we try to generate hydrogen or produce hydrogen by heating H2O vapor at very high temperature instead of electrolysis, how much hydrogen can be produced? That is our target. So now what we will see that hydrogen, whether at all it is feasible, economical to produce hydrogen in this method. Okay. Now see that this reaction is H2O is converted to H2 plus half O2. At the specified temperature and pressure, we are considering. Temperature is given as 4000 Kelvin and the percentage and the pressure is 10 kilopascal. The percentage of water vapor that separates into hydrogen and oxygen to be determined. How much it is possible. Assumption, we are assuming that equilibrium composition consisting of H2O, H2 and O2 only, because we do not know that whether it will be only hydrogen and oxygen at the chemical equilibrium condition. We do not. So, since it is not known, what we do is we assume it that it will be like this. Excuse me. Okay. Next, what we do? Therefore, we can write the stoichiometric reaction because the stoichiometric coefficients are to be known. Therefore, we have to write this. So accordingly, nu H2O is 1, nu hydrogen is 1, nu of O2 is 0.5. From this, how? Now actual reaction is not like the stoichiometric reaction, because actual reaction at the equilibrium composition, it will be including the reactants as well as the products. So you see that reactants left over, that means when we heat H2O in the equilibrium at the equilibrium condition, H2O will also remain. As I was telling, the total number of mole will be considering the reactants as well as the products. So this is this. So reactants left over and the products. So now what we can do? We consider that as if by heating 1 mole of H2O, we are getting X mole of H2O left over and Y mole of hydrogen and Z mole of oxygen. Now, as usual, we will go for mass balance. And after mass balance, you see that X, Y, Z, there are 3 unknowns. Now, how many equations we can write from this? You see that H2, hydrogen and oxygen. So we can only balance hydrogen and oxygen. So maximum 2 equations we can write. So 3 unknowns, it is not possible. Therefore, we will try to write all the equations, all the equations in terms of, that means X, Y, Z, all these we will try to write in terms of X only. Okay. So from hydrogen balance, we can write a relation between X and Y. So I can write Y in terms of X. And from oxygen balance, I can write a relation between X and Z. And therefore, I can write Z in terms of X. Okay. So it is clear. Next is in total we are writing. In total is equal to, therefore what? In total means at the equilibrium condition, the total number of mole. You see this highlighted part. It is X plus Y plus Z, total number of mole. So this is the equilibrium composition. So total number of x plus y plus z. Therefore, since I have written already y in terms of x and z in terms of x, therefore I can just combine all these x, y, z in terms of x only. Therefore, total number of moles is equal to this 1.5 minus 0.5 x. This is in terms of x only. It is unknown. That x we have to solve. That is our target. That means what is the mole fraction of hydrogen, mole fraction of H2O that is left over. Therefore, the remaining will be converted into hydrogen and oxygen that we can calculate. Now, the total, the partial pressure, the pressure is equal to 10 kilopascal. Okay, so this is the total pressure. Total pressure. So total pressure at this condition, that is low pressure. So we can convert this atmospheric the kilopascal into atmospheric pressure, because the total pressure will be in terms of the atmospheric value. Okay, the tabulated one, that is in terms of atmospheric value. Now what we will calculate is the equilibrium constant for this reaction H2O at 4000 Kelvin. We will see from the table that we have just referred. So we will see it. So for H2, this one. Okay. Now we will see at 4000 Kelvin. 4000 Kelvin. This one, you see, this value. 4000 Kelvin. So it is minus 0.542. Okay, minus 0.542. So that we have written. So that is the logarithmic value of the equilibrium constant. So if I just calculate the equilibrium constant, then we will just raise this, means it will be e to the power of this. Therefore, e to the power of minus 0.542 will be this one. Okay. Next, what is the target? Kp is already known. So in the earlier reaction, in the earlier relation, what we have seen, this one, Kp in terms of this one. This one. So Kp is equal to Nc to the power Vc, Nd to the power Vd, that is nu d, Na to the power nu a, and Nb to the power nu b. P by N total. Okay. Now here you see that instead of A and B, here only one reactant is there. Therefore, in the denominator we have only one. So we have written in terms of that. So that relation we have written P by N total. Okay. Now we see that we have just written Kp value here, and this number of moles of H2, number of moles of oxygen, number of moles of H2O, etc. we have written, and P by N total. So P is that pressure, total pressure. So that total pressure we have written here. P is the total pressure that is given, the given pressure. Okay, and this is 1.5 minus 0.5 x, that is already calculated, total number of mole. Okay, next you see that this is a relation which can be solved by trial and error, because you see that that is a non-linear equation. You cannot that is not easily solvable. So you can just write the equation. Okay, so after this, what we can do is we can get by trial and error we can get this x. So trial and error you can do by hand calculation, or you can solve it using some program. Okay, so what is the relation? Can you just see? The relation is, I'm just writing this relation. It is just like, just let me write that relation, just simplify the relation. It is 1 minus 3x plus 3x square minus x cube multiplied by minus uh, sorry, multiplied by 1 minus point, that is basically uh, I will I will better write this 1 minus Kp square by P, that is pressure, okay, is equal to 0. That is the relation. That is a non-linear relation, and we will try to solve it by trial and error method. Okay. Now, I will just show it how to solve. You see that this is a FORTRAN code that we have written, that I have written. Now I will try to solve it by trial and error. So what we are doing is trial and error in this trial and error. So I am just writing this x in terms of the remaining. So x is equal to what, therefore? X is equal to 1. I'm just taking it on the right hand side. So it will be 1 plus 3x square minus x cube multiplied by 1 minus Kp square by P whole multiplied by 1 by 3, because it is 3 multiplied with x, so it will be 1 by 3. So now I have just written this x. So what we will do in this trial and error, you see that both the sides are basically having x. So on the right hand side, I will guess some values of x, and on the left hand side, I will check whether the value that I have guessed is matching with x. Okay, so uh, that is the mechanism or method of using the trial and error. So on the right hand side, I will guess some value of x, and I will calculate that again whole right hand side. Since this is only x, therefore these value must match. So if they do not match, then I will again refine the guess. So that is the trial and error. Okay, is it clear? So trial and error means I am guessing some value, and I am verifying that whether the guess is correct or not. If this is not correct, then I will again refine or correct the guess. That I will continue till I get the correct or converge value, when this right hand side and the left hand side will be matching. Okay, or the difference between the right hand side and the left hand side will converge to a particular tolerance limit, because they will not exactly match numerically. So I will use some tolerance, that is the difference between the right hand side and left hand side, and therefore I will calculate the difference. If the difference goes to a particular limit, below a particular limit, then I will stop the calculation. Okay, now I will do it. You see, can you see the uh, code? Okay, so what I'm doing is I am using this one. So G means the guess. G is the guess. So I have guessed some value 0.1, and I have used the guess as equal to x. Now I have written the right hand side as C. C is equal to the right hand side, that is 1 by 3 is multiplied by that. And this one is the term that is 1 minus Kp square by P, that I have calculated for this particular reaction. And this is like this. Okay. Next, I have printed it to check that whether they are same or not. Now I have taken absolute value C minus X, that is the correct value, on the right hand side minus the left hand side. If it is less than some particular value, I have taken a large one. So you can assume some very small, say for example 10 to the power minus 5. Okay, and this increment also you can take some value like 10 to the power minus 5. Okay, and if this is greater than the tolerance limit, that means the error is more than this value, then it will again continue with the correction. So that way it will continue. Okay. Now I will run this to check how much it is coming. Since I have just printed all the statements, that is why it is taking a longer time. Now it is converged. So you see that the converged result is 0.2222, right? So converged result is 0.222. That is x is equal to 0.222. Okay. So I will elaborate about the code later in a tutorial class. Now just take it as it is. So it is like this. Okay. Another code that you can use is this one, where I have guessed some value. Next, what I have done is, as usual, I have taken x is equal to the guess and then calculated the value of c based on the guess, then printed it whether they are same or not. Next, what we have done is I'm checking the absolute value, that is c minus x is greater than some limit. If it is greater, then what I am doing is I am assuming that the guess, I am assuming that the calculated value as the guess. So this is the calculated value. I am assuming that guess is equal to the calculated value. In the earlier one, I was just incrementing the guess with some arbitrary value. But here I am directly assuming that value to be equal to the corrected value or the calculated value. So here also it will give the similar result. Okay, just check it. I will send the code and you will also be able to try it. Okay, you see that 0.2222 that is coming. So it is correct result that is coming. Okay, next we will see what is the outcome in the problem. So it is seen that it is 0.222. So our result is correct. 0.222 is coming. Again, you see that this is the cubic equation. So actually there will be three values, three roots for these values. So to see that, what we have done is I have graphically tried to show it. Okay, I'm showing it. Now I have written this in Desmos, uh, the graphical relation. Remember that this is not for your exam, because in the exam, definitely this type of calculation will not be there. So just for your understanding, I'm trying to show. So this is the relation that is simplified like this. So this is equal to 0. Now I have to calculate basically I have to calculate the roots of this equation. Now I have plotted it here. You see that red line is the plot for this graph. So you see, now I will try to show you that what is the value. You see that one root is here 0.56, about 0.56. So x cannot be 0.56, right? X cannot be 0.56. Again, this is how much? Can you see? About 0.21. If I just make it zoom, then I will be able to show you. So it is 0.22. Can you see? 0.22, 0.222. Or if you further zoom it, then also
Yes, sir.
then it will be much clear. So 0.2225, like, right? So this is this one. Next, the third root that is here, which is how much? 3.34. This is also not possible, because this is your means more than 1. So mole fraction cannot be more than 1, isn't it? So it is also not possible, minus also not possible. So this one, that is 0.222, that was calculated. This is the correct result. Okay. Now by trial and error method, you can arrive at this location or at this location depending on the starting guess. Okay. But if you guess, if you get these two, then you will basically discard this and you will take this value on. Okay. So that is the solution for this. Now I am just returning to the solution for the final time. Now you see that x is equal to 0.222. Therefore, what is x? X is this, therefore hydrogen. Therefore, hydrogen is how much? So sorry. So dissociated H2O is how much? Therefore, it is 1 minus x. So x is undissociated H2O. Therefore, dissociated H2O is 1 minus x. So therefore, we see that it is basically 0.778. That means during this, that means at 4000 Kelvin, if water vapor is heated, then 77% of H2O vapor will be converted to hydrogen and oxygen, dissociated to hydrogen and oxygen. And remaining 22.2% will be remaining as H2O, undissociated. Okay. Now I will give you one task. I will send you this code. Okay. This FORTRAN code I will send you. You will uh, get Force 2.0 from website, internet. You will get. You will download it and install it and run this code for different values of the uh, equilibrium constant. That means at different temperatures. So what my target is to show you that what will happen at different temperatures. That means at 4000 Kelvin, it is clear that how much water will be dissociated. Now at, say for example, from 298 to 4000 or 298 to up to say 6000 Kelvin, what will happen? So you will simply write that value of the equilibrium constant there. Okay. And you will calculate what will happen. You see, sorry. Uh, yes. Now here you will just replace Kp value, and for different temperatures, you will be able to calculate the value of X for different temperatures. And you will understand that with temperature change, what is the rate of dissociation or what is the fraction of dissociation. Okay, that you will do as assignment. Okay, is it clear? I will send you the code and you will be able to solve it. Okay.
Yes, sir.
Okay. And if any means help is needed, you can call me. Okay, I will send you the code as well as the FORTRAN that is software, or you can also download it from internet. That is Force 2.0. The name of the compiler is Force 2.0. Maybe it is 2.09 or like that. So the after installation, it will look like this, Force 2.0, but actually the version is Force 2.09. Okay, G77 like that. So you will install it. It is it will take very small amount of your hardware space, hard disk space. It is about 2 megabyte the application, and after installation, it will take very small yeah, that is space, so you can easily check. Okay, and by this way you will also learn how to write code in FORTRAN, because the FORTRAN is uh, used as scientific computational language, so you will be familiar with FORTRAN also. Okay, later we may use some other codes for writing, other languages for writing codes. Okay, so I think we can stop now. Okay, are you here?
Yes, sir.